observations came up. For example, initially we had this Julia set as a big black blob, people call it a bug, and then when the bug became more precisely drawn, there was all kinds of junk around it. Now, the junk might have been anything. For example, part of the junk was just a very poor computer system we had. In fact, it was a miserable system. So what we did was to act like a naturalist, like somebody 18th century botanist or zoologist. You take a microscope and look closer to see what happens. So we looked at some of these little pieces of junk by magnifying the Mandelbrot set, and they vanished because they were just junk. And others did not vanish. So as we did it, something quite extraordinary came up, which is that if you magnify a small piece of the Mandelbrot set, that piece looks like Julia set itself. So the whole Julia set has a kind of, say, miniature version of itself in the Mandelbrot set. And after a few weeks, we had this very strong, overwhelming impression that this was a kind of big bear we have encountered. I think the most important implication is that from very simple formulas, you can get very complicated results. It's fundamental from viewpoint of the very base of science, because what is science? We have all this mess around us, things are totally incomprehensible, and then eventually, more or less rapidly, more or less hard to achieve, we find simple laws, simple formulas. In a way, a very simple formula, Newton's law, which is just also a few symbols, can, by hard work, explain the motion of planets around the sun and many, many other things to the 15th decimal. It's marvelous. A very simple formula explains all these very complicated things.
There's an interesting parallel with the equation that almost everybody is familiar with, the only equation almost everybody is familiar with, E equals mc squared, Albert Einstein's equation that says matter and energy are equivalent to each other. That was a very simple equation with very far-reaching consequences. And the equation for the Mandelbrot set is equally simple. Z equals z squared plus c.
The letters in the Mandelbrot equation stand for numbers, unlike those in Einstein's equation where they stand for physical quantities, mass, velocity, energy. The Mandelbrot numbers are coordinates, positions on the plane, defining the location of a spot. Another difference from Einstein's equation, and a very important one, is this double arrow. It's a kind of a two-way traffic sign. The numbers flow in both directions, constantly feeding back on themselves. This process of going round and round a loop is called iteration. It's rather like a dog chasing its own tail. The output of one operation becomes the input of the other, and so on and on and on. When the Mandelbrot equation is given a number representing a point, and that number is iterated through the equation, one of two things happen. Either the number gets bigger and bigger and shoots off to infinity, or it shrinks to zero. Depending on which happens, the computer then knows where to draw a boundary line. So what we get from this basic iteration is a kind of map, dividing this world into two distinct territories. Outside of it are all the numbers that have the freedom of infinity. Inside it, numbers that are prisoners, trapped and doomed to ultimate extinction.
Think of a computer screen. You're looking at each individual little element, each pixel of the screen. You pick one of these pixels, you apply this rule lots and lots of times, and either the pixel moves off and disappears completely from view, or it moves in towards a fixed point in the middle of the screen. And what you do is, you just want to distinguish between going off out to infinity or going into zero. So any point that moves into zero when you apply this rule, you colour that point black. And any point that goes off to infinity, what people tend to do is colour it all sorts of wonderful rainbow hues about how fast it goes away. The important bit's the black bit in the middle. That's all the stuff that doesn't escape when you keep applying this rule.
Now, the colours are completely arbitrary. They could be anything, but they are not meaningless. A very good analogy is the contour map, you'll see, of a mountain range, for example. where the contours are drawn and colored, the areas are colored. The highest areas might be colored white and brown, then green. And then if you went on into the sea, deeper and deeper blues, just to show where the various levels occur. So it's the same here. You can make the colors anything you like, but they do define the different areas of calculation. And you can change them and get the most gorgeous results. Just look at this. Now, you may think that the frontiers are moving, but there's no motion whatsoever. Only the colors are cycling, in or out. Nothing is moving.
When you get very, very fine to very, very small details, the variations can become of overwhelming complexity. So complex that no single picture can possibly give justice to them. It's impossible in a black and white or color picture to show how complicated it is. The only way is to use what we call the color cycle. That is, the colors change regularly, and each set of colors in a way reveals a different property of these variations, a different variation. So by having this color cycling, one reveals in a very, very strong fashion the extraordinary complexity of the set. If the whole set were represented at this scale, the end of the set will go so far as to go somewhere near the star Sirius. Very, very far, enormously big, for this very tiny speck. Yet in the middle of the speck, you see an exact replica of the whole.
One of the most striking facets of the Mandelbrot set is the internal consistency of the object. It all hangs together. And if you look at the boundary and zoom in, if you look in just the right place, what you see is baby Mandelbrot sets, perfect in every detail. They're just slightly bent compared to the real set. You can't even see that, but if you look closely, they are. And they're decorated by slightly different external features. And then by the same token, if you zoom into the boundary of those, you see baby Mandelbrot sets, the second generation. And inside those, the third generation. It goes on forever. And so you're seeing islands of order in a sea of chaos.
I'm sure it's occurred to you that the Mandelbrot set looks like some kind of strange insect. It certainly has an organic feeling about it. It's got warts all over it, and it's also quite hairy. If we go out along one of those hairs, we find something rather interesting. Now look what's happening. At the tip of each hair, it splits into two others, and so on. Each is splitting, going on indefinitely. This splitting up, this bifurcation, going off into apparently random directions quite abruptly, is typical of a class of mathematical entities called fractals. The Mandelbrot set is the most famous fractal.
The word fractal means any geometrical structure that has detail on all scales of magnification. No matter how big you make it, you still see extra new details you didn't see before. And the name was actually invented by Mandelbrot himself. He felt he had to have a name for this area he realized he was working in. And so he coined the term fractal because it